Hey guys, before I read this problem off for you, I want to at least get into the motivation or the idea behind calculating this prime factorization. I just wrote it down. I didn't want to go through each step of this, but uh, to count the multiples of 2, first of all, let's observe that 11, 13, and 17 clearly appear once if you just think of what 18 factorial means, right? You run into 11, 13, and 17, and they're the only multiples of 11, 13, and 17 just because of the size here, because of 18 factorial. But what about 2, which occurs like crazy, you know? There's this cool result using floor functions, okay? And y'all, just formally, what this statement is saying, it says count the multiples of 2 less than or equal to 8. That's what this symbol, very nice, curt little symbol means, okay? And you could do that without the floor function, right? I mean, it's clear there's 9 multiples of 2 less than or equal to 18. Now notice 4 and 8 and 16 are getting counted in this thing, and that comes into what's the idea, the main idea behind this result. It has a fancy name. I can't remember what this is called. But so what we do, because of what I just said, is you have to count. You have to do this for 4 in the denominator, okay? So we have 18 over 4. And again, folks, if that's not clear to you, it's kind of beautiful how this works out. If that's not clear to you, remember 4 got counted already. I mean, 4 didn't get counted. It only got counted once as a multiple of 2, right? But it actually, there's 2 copies of 2 and 4, so that's why you have to do it this way, okay? Now here, 18 divided by 4 gives you 4 with a remainder of 1/2. And so this floor function, this greatest integer function chops that off, so you get 4 here. Okay. Now, similar argument for 2 cubed. Okay, so you have 18 over, and this is kind of neat. The proof of it, I guess, is sort of tedious, but it's pretty easy to believe, right? Okay. Now, this would just be 2, right? Again, and the multiples of 8 less than or equal to 18 is manifestly 2 without using this formal thing. Now, we get to the next one, which would be 2 to the 4th, which would be 16. And so you get this. And that's just 1, right? Now, y'all, the next one would be equal to 0, and I'm just going to write that out there. This does have a terminate condition. The next would be 32, right? Well, 18 over 32, clearly there's no multiples of 32, so you expect that to be 0. But 18 over 32 does have a floor of 0, okay? So anyway, note that this does add up. Let's see, 1 plus 2 is 3, 7. That does add up to the 16 that you see right here, okay? And again, I'm not going to go through it for 3, 5, and 7, okay? But this is the prime canonical factorization of 18 factorial, which is important because we're talking about divisors and multiples, right? All right. So we're trying to determine the largest multiple of 18, which is a divisor of 18 factorial. And I said that in 2 senses, 18 factorial, and this is fascinating. All right. And then having exactly 18 divisors, right? All right, so it's kind of cool. A lot of 18s flying around here. Now, one thing, a good way, in my humble opinion, to get started is it has to be, whatever we're going to get as an answer has to look like this, because bare bones minimum, it has to be a multiple of 18, right? But 18 is 2 times 3 squared, right? 2 times 3 squared. All right. Now, notice the M does have some conditions on it. It can't be any larger than 17. It can be 13. It can have divisors of 13, 11, 7 combinations, 5, you know. But you can't go any higher than 17, which is useful to just keep that in mind, even though it's obvious, right? And also, we're going to use this pretty famous result about counting the divisors, which says all you have to do is increment the exponent. That's essentially true because 0 has to be allowed as an exponent. Okay, I won't say any more about that. It's a well-known result in number theory. Okay, now I just listed out, this is the first one that came to mind because 17's big, right? But notice that there's 5 ways to have written this, right? There's 5 ways, 5 possible ways to write it, because I just as well could have replaced 17 with 13, 11, 7, or 5, right? So this represents 5 possibilities, sort of. I didn't go to the trouble to be formal about it, but I just chose the largest one, okay? And notice it does meet this condition here. There's an understood 1 right here, right? And so you get your 18 divisors. So this is a possibility for the largest multiple of 18, which is a divisor of 18 factorial, okay? It's a possibility. But then you always think about exponential growth and you realize that 3 to the 8th, and it doesn't take too much trouble to show this is a bigger number. I do take the time to do that. But notice it also in a different sort of way has 18 divisors. 2 times 9 is 18, right? So this is an other candidate, right? And I guess we could have written that as, could we have written it as, no, we can just have 2 once, right? Yeah, we only have, or wait a minute. Maybe we could write that as, 2 to the 8th, but 3 squared, but that's a smaller number, right? So there is another possibility here too, right? But this is going to be the largest one, right? Okay. Now, again, another possibility here, which is clearly going to be smaller than this number, right? Another possibility because it's in our form, okay? And you get your 3 times 6 happening here, which is 18, right? So the only debate is what is the, and again, I haven't listed everything exhaustively. These are just the highlights right here. So which one is bigger amongst these? Well, we know that this one is out of the picture, right? Because it's smaller than this one, right? Now, a real simple way to see, without using a calculator here, a real simple way to see that this is the largest number is just to make this observation right here. Well, I'm just stating it's true. But it's true because you can just steal 3 squared away, and then right here, 3 cubed is 27, and you would get 27 squared right here. Right, folks? This is a nice way to do things without even knowing any idea what 3 to the 8th is. I love this. This is pure appealing to the results of just exponentials without having to do calculations. But you see, here's your 17 squared, and 27 squared is bigger, right? So that settles it. This is our champion here. Okay, and y'all, I did take the time to use the calculator just for the sake of, even though technically in a competition I think you could leave the answer this way. This would be 13,122. Okay, let's be sure we know what we just found. This number is the largest multiple. Let me see, is it still on the screen? Yes. It's the largest multiple of 18, and it's clear that it is a multiple of 18 because of its form alone, right? 18 is a divisor of this object right here, right? Okay. And it has exactly 18 divisors, which we showed, right? So it's all there. It's all there. So 13, I'm pretty confident that 13,122 is the answer, although there are other possibilities I didn't go through, but you can just tell by the form. I picked the ones that were the biggest one of that particular form, okay? Now, you may be saying, well, why didn't you consider, we know the number of divisors of p to the 17. This is also a very basic result from number theory. The number of divisors is 18, so it would meet that. But we're not dealing with a p, we're dealing with 18, which is not a prime number, right? So this is not something, you would think about it logically, but it doesn't apply to this. It won't fit here at all, okay? So anyway, 13,122 is the solution to this problem, folks. Or at least based on the way I went through it, it is. Okay, so that's our insert. 13,122, and again, I don't mean to harp too much, but with the time constraints of a math competition, they'll let you leave your answer this way. I think anybody, I don't think they count off of anything. You get full marks, I would think. You can check with Way 10, the SMO guy who's a coach, and also was a very accomplished competitor in those SMO competitions, and I think he got a very honorary degree from the national school there. Okay. But anyway, this is it. Goodbye.